No, but how, no, I know, but how is this actually, how is this an if statement? This does not look like any if statement I've seen.
That's condition and then there is
Yeah, I know, but how, so this evaluates to a Boolean. And Boolean is it evaluates an object. And then you send that object, whatever object comes out, you send that object a message with two parameters, right? A then block, so these blocks are basically, they're what are called, I mean, they're pieces of code. Right? You think of them as lambda expressions or just on-the-fly functions. So you're sending it a block of code here, which is, again, an object, and you're sending it another parameter, which is another block of code. So it's like you're basically sending the Boolean object a message send. And this message send will dynamically dispatch two different implementations depending on if this is the true object or the false object, right? What does the false object do? Well, the false object takes these two things and evaluates the false block, and the true object evaluates the true block, right? So it's a very interesting way of thinking about if statement. But of course, it's also ridiculously expensive. I mean, you're doing an if statement now, it's like, I mean, an if statement in C gets compiled down to like a branch in x86, right? It's super efficient. This is very, very expensive. So it's cool that now that they do type prediction and all this stuff, they can start inlining it, and it's kind of this, you get this effect that every step you inline something else, and you get all these things, and at the end of the day, they're actually able to generate something that's almost as efficient and looks almost like a C code. Now, when you look at the final thing, actually, it's actually not like the C code. It's actually much uglier. And you'll actually notice that part of what's really nasty here, unless if I read this correctly, right, there's a whole bunch of, so really what they do is every time around their loop, they actually have to check for whether or not these different things are of the particular type that they expect them to be. And then if those things are of that type, then they basically have the optimized version. But they have to do those checks every time around the loop. So that's one source of inefficiency here. So actually, in general, if you want to do this, the kind of thing you want to do is you want to hoist those checks out of the loop, right? You want to pull those checks out and do them once at the top of the loop, saying if this is an integer and this is this is a common case, then you can optimize based on those assumptions. Does that make sense? Does everybody follow? So that this is basically all these checks, and these are the checks that have to do with the assumptions about types that they made when they do the specialization. Okay, so what's the other thing they did? So in addition to specialization, they do this thing called splitting. Do you guys remember what splitting is? So what's splitting? Wait, where's splitting? So this is the example they have. Basically, it's that, this is, you have this fragment. Now okay, again, what are we doing here? You have to make your brain kind of parse this properly. That's a test, 0 equal to I. That's like, you're basically, you're essentially sending a message send of equal to the 0 object with I as a parameter. You're getting a return value back, and you're calling the if true message or whatever object that is. And what happens is that if this is an integer, this I is an integer, then you can inline the implementation of that check. And that implementation for that check for integers is literally equals I, right? That's like the integer, that's like we're back to like, okay, like, this is like the mathematical kind of like, equality test for integers. And if this is true, then you set this to true, that's the true object. And otherwise you set the false object. Otherwise, well, basically they're like, they just give up. But the point is now, once you've done this, now you call if true, but the problem is here, you can't inline if true, right? Why can't you inline? Because you don't know it can either be true or false, so I don't know which implementation of if true I should inline, right? Does that make sense? that have two different things that come here. And so the trick that they play is that they take this message send and they copy it back they push it up into the branches, into all the branches. And so what happens is this gets copied at the end of this else, at the end of this else, at the end of this else. And the key thing is now at the end of this else, I know this is true. So it becomes true, right? Temp is true. So now you basically know that this is true, and now you can inline this if true, right? And then here you know it's false, so you can inline this if false. Okay. Are you guys seeing this? I'm doing all the talking. This is not fair. You guys are supposed to do the talking. So, what else was there in the paper? Okay, so do people like the paper? What was cool about it? No? You didn't like the paper?
What was cool?
What? Okay, you didn't like the paper. Okay, well, we have one data point.
If you ignore the stuff about the cell phone, you get this. But there's a part of that commentary that was
Wait, the self-language, you mean you don't like the self-language?
Right, I'm not interested in that part. That's very cool, especially
Self-language is so...
25 years later.
So I should point out, by the way, the reason... let me just say one thing. Let me just give you another... Let me just say another reason why this paper is interesting. So the self-language is very much inspired by Smalltalk. I mean, Smalltalk has a very similar kind of, conditional. That's how conditional is done in Smalltalk. And in some sense, Smalltalk was kind of was basically introduced the idea of OO. So, I mean, everything that comes after that was kind of, the lineage comes from there. So in some sense, I mean, it's also interesting to see kind of where these OO ideas originate from. And this is, the idea here is that everything is pure OO, right? True and false are objects, and they have methods on them that you call, right? I mean, it's like everything's really object-oriented. And it's actually really cool that by pushing this whole paradigm so far out, you can actually even implement if statements. Right? Basically what they're doing is they're using dynamic dispatch to implement control flow. So it's actually kind of, but okay. So, okay, that's okay. Yes.
I think, it's got some good ideas in, but I don't think that they communicated them in a very easily accessible way.
Sure.
Like, it took a while to understand what they meant by objects. Maybe that's because
we've been polluted by decades of sure, I agree. I mean, Zerver's right. So Zerver's have objects. So right. I mean, what they mean by objects. So they don't. By the way, they don't have classes, right? So that's kind of an interesting thing too for the self-programming language. I mean, they don't have classes, which is an interesting thing that you can. They have what they consider to be a super pure OO language with no classes. Now, of course, that's kind of a lie because they do have. They figure out the classes afterwards, right? They have these maps that kind of map to these things that are, there's common pattern that they observe. What? Not even that. I mean, they don't have, it's all dynamic. There's no concept of like, it's just, it runs.
The maximum number of
Sure, but the compiler figures those things out. It's not like the programmer is aware of these things, right? So, yeah, all those things are actually compiler generated. So all those things is based on where you actually, where the parents are, right? So basically, you create a prototypical point, which is your kind of the point that you will stamp everybody from, and then you just make everybody kind of be what is it called? Have the parent link point to those, and then they're gonna infer that that's kind of one of these things that kind of represents the type of all those things that point to that parent. But you're right. I mean, I'm not saying that I just point out this is what happens with research papers a lot of times. I mean, you have to kind of this is why you have to. It's not easy. This is why we're doing this in a class, right? Because it's not. You have to read the paper, and understanding the paper is not always easy. There are challenges. So kind of getting through to the crux of what matters is not always easy. You're absolutely right. And the authors don't always do the best job, but yeah. What else? Yes.
I like the runtime type test that they do little tests and then see on those tests what are the types, and I think that maybe that's a common case. And then
they can specialize.
Right.
So it's like they can basically say if this is an integer, then I know it's integer, and then you can actually optimize based on those things.
Right. So they like run your program on their input first and then on your input. For the type test.
Right, and you can do profiling where you can run out a whole bunch of things and see what the common types are and then predict that, oh, I want to specialize. So specialization is very important in all languages, which basically means I assume it's going to be a type, and I'm going to optimize my code like really a lot based on that assumption, and then I'm going to put all that code in a branch that says, if it's that type, then I can do all this stuff. Yes, and yes, but you go first.
Is it fair to say that they basically trade code loads in the binary for performance?
Yes.
Like all of these things?
Yes, to some extent, absolutely.
How much
Right.
of an issue was that at the time? Like, was there a way to drop the parts that they definitely didn't need, or?
Right, so as you may have seen from the benchmarks, I don't know how many of you looked at the benchmarks, but the benchmarks are really small, right? They're like, what?
400 and 900 lines.
Yeah, I mean, it's like, compute the average, compute the sum of, so we're laughing now, I mean, I was just saying, but this is like, this is the 80s, right? I mean, this is a long time ago, I mean, I'm just saying, like, things change, right? So, at that time, they weren't that concerned about it, but part of the problem is, for some of these things, actually, the code blow doesn't hurt you that much. I mean, the problem is, the message sends really kill you, right? And so that's where some amount of code blow helps. Now, there are some of the things that are the most successful and that have been applied broadly are things that don't do code blow. For example, the inline caching and the polymorphic inline caching, those don't really create code blow much, right? I mean, basically, you're just kind of patching the thing to go to the right thing, and then you're inserting a little bit of a check there.
That's like a constant increase in,
Right.
in code type, where everything else blows up by like your universal possible type.
Absolutely, absolutely. So in that case, getting the type prediction right is very important. But I should point out, actually, so part of what's going to be cool is part of what I'm trying to do here, and I don't know how, it's like, we're seeing, this is a paper from the 80s, and in a week from now, we're going to talk about, like, the state of the art in terms of these dynamic things, which is JavaScript and in Firefox. And so there we're going to see an alternate way of actually doing these, adapting for these kind of dynamic things. And JavaScript is a problem because you don't know, again, there you don't have types, so how do you actually, right, I mean, how do you know? And we'll see a different kind of approach, which is inspired by this, but it's actually different. It's called trace-based JITting, which is, yeah. But the point is that, wait, what? The point is, a lot of what you do is you dynamically, in real systems, because these things dynamically, you're going to look at the types that are important. Okay, those are the most important. And in practice, there aren't that many actually types, that many possible targets. So actually, we did a study on Chrome, and we looked at the C++ virtual method called in Chrome, and on, when you look at a particular method call, how many possible things could it go to at runtime? Like when you run it, forget about I'm not talking about statically you look at this is at runtime, and it's actually not, there's only a handful on average per call site. It's not like you get 10 or 20 different possible types that can go there. It's actually only a very handful, a small number of types per thing. So, yes. Okay, does that make sense? So in practice, you dynamically instrument things, look at how many types you have. If you have too many, you give up, but if you have only a few, then you can do good things.
You still always have the default fallback.
Of course.
So, I mean,
Yes, you can always just give up.
They could go a step further and say, I'm going to try this, especially nowadays, we have plenty of time to compile it, compared to running, where they could say, I'm going to try this with 10 different or 100 different types. If there's a big speed up, I'll keep it. The ones that don't really change much, okay, go back to the
Right, exactly. But the truth is that a lot of what these systems do today is actually they don't do that. What they do is they do everything dynamically, where actually the compilation cost really hits you. And what they do is that they use dynamic instrument to see which are the hotspots, which are the areas that, and which types matter. Right, you're going to determine that actually I really need to optimize this for this type, and then you just do it then, and then they're on demand for that type. Okay, yes.
Is it also doing just-in-time compiling?
So
Sentence that seems like they are.
they are. I mean, well, okay. Yeah, I mean everything everything they're doing is just in time, right? I mean it's all. I mean, so first of all, they're doing. Yeah, I mean, I think if I remember correctly, I think it's
Is the first line in section 4.1?
What?
The first line is section 4.1.
Yeah.
Previous compilation is
Yeah. Wait, hold on. Are you saying that yes, they're doing everything?
Yeah.
Yeah, absolutely. They do everything dynamically. This is like a JIT. I mean, it's all dynamic, right? I mean, they're all just like taking this stuff. Now, the point is, in this paper, they're not talking about. It's a follow-up optimizer where they really start like looking at collecting information about what parts are hot and really optimizing those a lot more. And that's where those ideas came. The hotspot compiler. That's where that came from for Java. From the line of work that came after this. It's the follow-up paper. So yes.
So they do something called as per method-based compiling, that is online compiling, and there are strategies dump everything during compile time, that type checking and all. So that increases the compilation time. So doesn't that hurt their original intention to increase the performance?
Wait, say that again?
So the strategy is to dump everything during compile time.
Right.
To the type checking stuff.
Uh-huh.
And the compilation is online compiling.
Right.
So, and doing everything during compile time increases the compilation time.
Right.
So doesn't that hurt the original intention to increase performance?
Yeah, I mean, basically, it's one. Well, so yeah, I mean, basically, what you're saying is that because they're doing compilation at runtime, I mean, that's going to hurt performance, and absolutely. But really, what their philosophy is so the philosophy that they're having here is more that we have this system that's super dynamic, super cool, and we love it. They love it, and they're like, but it's really slow, and we want to make it faster. And maybe we can't make it as fast as C, but we just want to make it faster than the current like really slow thing, right? And this entire story that I said, that's exactly the story for JavaScript, right? It's like, there's this language, we really love it. It's like everywhere on the web, but like a few years ago, 5 years ago, like it was like really slow. So people were like, well, we need to make it dynamic, and also we want to make it fast. So same kind of motivation. And yeah, absolutely, you're giving up, you have to compile, but there's no other way to do it. Because you have no types, it's really hard to optimize these kind of languages statically. I mean, there's just, your hands, it's really hard to do statically. Okay. I'm going to cut this, one last comment. And then we move on, because otherwise, I mean, we're never going to, this is such a cool, no. Okay. It's so cool that we'll keep on talking about it.
So these techniques are very generic so that they can even be used today.
Use what? Use strategies?
Yeah. These techniques are very generic.
Yeah.
So many of the, most of the techniques, the optimization techniques can even be used today in many different kinds of languages.
Not in many different kinds of languages. They're used for languages that are dynamically typed, object-oriented, prototype-based languages.
Okay,
Which JavaScript is a great example. But also some of the optimizations in the Java virtual machine also take inspiration from here. For example, the find more frequent caches and all these things. Those are things that also are useful, that were actually in the small file system before. So they weren't just stayed in the event teams, but they were there before. Those are actually really useful in these dynamic systems.
Okay, so in the type prediction section, that all the techniques produced by the author based on the measurements of the Smalltalk 80 benchmarks. Is it also applicable for today's? I mean, all these features of Smalltalk 80 are also the features of today's the language like JavaScript.
Well, I mean, I should say it's the ideas I mean, the point is, yeah, I mean, a lot of these optimization ideas really are at the core of what you need to do for JavaScript, or at least what some people have chosen to do for JavaScript. That's the Chrome the V8 has done something that kind of is really heavily inspired by this. The Firefox people then have a trace-based, kind of a slightly different approach, but we'll talk, and that's part of the thing, we'll talk about that next time. But the point is, the details of, this is like more like the old, this is like the seminal papers on this stuff, right? This is where like these ideas were completely wacky at the time, right? This is like, people were looking at this like, this is weird, ridiculous, what is this stuff? And lo and behold, I mean, this is what's interesting, lo and behold, all of a sudden, we now have the same weirdness running everywhere.
I think that's part of the reason why this paper was a little bit tougher. Like, I read the whole method study, secret column, I'm like, it's different. And then I had to like kind of.
Well, method send is a virtual method call.
Right.
But it's important, I mean, this is a historic. You know, by the way,
language today, that's.
but you know, Dave Unger, this guy, Dave Unger is a great guy, he's really, actually, but, you know, from his perspective, he's like, dude, you guys have these weird names for everything, right? It's like a message send, right? I mean, because they actually came up with the ideas first. I mean, they named it, so it's a.
Because we have to roll back our minds, we're used to modern languages that people
Absolutely.
like already.
Absolutely. But now your mind is flexible, and when you see message send, you'll be like, whoa, I know what that is. Yeah, I mean, I don't know. But this provides a historical perspective on things, right? Cool. Next Thursday, we're going to read a much more up-to-date paper. You guys are going to, you'll hear words like JavaScript and Firefox. It'll be much more in your comfort zone. But still, but the point is that that'll be kind of updated version of all these ideas. Okay. What's next? Let me close. Oops. Okay, back to our lecture. Remember, you guys remember we were doing data flow analysis? This is the other super exciting topic we were doing, which is so much fun. Do you guys remember where we left off with data flow analysis? We did those. So what's this? This is reaching definitions. So remember, let's roll back. What? Right, we came up with these constraints. Exactly, the flow function. So let's go back to the history. This will be like, history of our data flow analysis lecture. So we basically start off by just saying, okay, we want reaching definitions, here's how we would do it. This is saying through an example. And then we actually figured out that we can compute it in a slightly more general way, which is that at every point we can compute this mapping of variable to the point where that value could come from. And then we basically use constraints to formalize the data flow analysis, and so we came up with these constraints for reaching definitions. And just to remind you, right, that the example is for x equals something, we basically removed all the in, we take a function, we basically are going to construct a function that gives us out in terms of the in, and what do? We remove all the bindings of x in here, and we add that fact that now x comes from x, right? So because afterwards, right after here, x will come from x. We also saw the pointer assignment, and then we basically saw how to do branches and merge is union. Branch, you just kind of copy things over. And so these are called flow functions. These tell us how the input and the output information out of particular statements are related. And then we came up with this. And that's where I think we left off. What's this? This is, so really what we're saying is, we want to solve, at every edge in the control flow graph, we want to solve one of these steps. So those are our unknowns. We give them names, D0 through D16, we give them names. At every edge in the control flow graph, we give it a variable name. And then these functions are the flow functions. So this flow function right here, FA of D0, is the, well, that's not good. Okay, that's... Rotate my screen?
Yeah.
Does that work? So I can set this D0 to the empty set, right? And that once that's done, what will happen? It'll be a ripple effect, where essentially from D0, everything will just kind of collapse, and I'm going to basically get an answer to everything. So in this particular case, that's that's kind of how this would work. Now, okay, let me just, so the reason why it works this way is because this is what's called a forward problem, which basically means that all of our flow functions tell us are in the forward direction. We'll see later, we'll talk about backwards problems later, but here everything is in the forward direction. If I know one thing, it'll tell me the value for the next one. Now, the incoming information, there's two ways to do it. One is what I just did, which is I basically literally set it to some value, which is the empty set. Okay. There's another way to do it, which is that you basically can have what's called an entry node. And the entry node is basically going to be a node in your graph, which just represents the fact that it's the beginning of the control flow graph. And there's no incoming information, there's only outgoing information. And I can write a flow function for this. And the flow function will take no inputs because there's nothing to input, and it will produce whatever should go out here. And this is an example of what this flow function should do. My pen isn't working anymore. I don't know why. Something's really weird with my computer right now. So what does this say? It says that out here we have x. What is this? Basically, we're saying that here we're going to basically put definitions for all of the formals, right? Because let's say it's a procedure. So the procedure will have a whole bunch of parameters like A, B, and C. And so here we're saying that where do those A, B's, and C come from? What's the definition? Their definition, we'll just make them come from the entry, right? Because they're defined here, right? When you enter the function, if it's a parameter, it's defined at the entry point. Does that make sense? Okay. So now we have this thing, and now we can basically, we can solve this thing, and notice how, so we can solve this in this forward direction. Now, another question that comes up is, so, in some sense, what's the order in which you have to define? So we take all these nodes. What's the order in which you have to process the nodes? I mean, I kind of like that. I know, but what does that mean? Okay. Let me wait. Suppose I have a control flow graph. Let me assume for now there are no loops. Okay. How do you compute the order in which to, is there only one order to process these in? What is it? What? Breadth first. I think breadth,
The topological sort.
Breadth first would work in this example, but actually breadth first is not the only, there are other things that are not breadth first that would still work. And who said it? Someone said it.
Topological sort.
Topological sort. So basically, really what you want to do is you want to take this graph and create a topological sort, which basically means the constraint of the topological sort is that at any point in time when you put a node in that sorting order, all the nodes that are predecessors of that node come before it. And the reason why you want that is because you want to have processed these two nodes before you process this one, right? So topological sort. So that's good. Fine. So what about loops? So if you do loops, oh gosh, what happens? What?
What would that even imply?
What would that imply?
In terms of like what code can produce a loop?
What code could produce a loop? Oh, it's a for loop. What do you mean? What? No, I mean, to make this concrete, what if this is oh no, but my pen doesn't work. Uh-oh. So what happens here? I don't know how I'm going to do this without my pen. I can use a board, but... So this is, I didn't quite understand your question. When you actually, you know what I did here, right? All I did is I added that extra edge, right? So this is basically saying maybe there's a condition, a branch here that says, under some condition, go back to here. Yeah?
I think we're going to need two blocks in the one loop.
We're going to need what?
So we're going to need two blocks to do this analysis on a loop. The first one, we know where variable x comes from, because it's serial, but in the second loop, x might be coming from an instruction that's ahead of time. That's not clear.
Right. Well, actually, no, actually, this does happen here. So, I mean,
Yeah, so our key is gonna, in the second loop, we don't know where x comes.
right. So, where does x come from now?
Well, if we're at the first loop, x comes from the first block. If we're in the second loop, x might come from start key or stop key.
From both of those. So, actually, what's the answer at the end of the day? At the end of the day, I want only one answer. I mean, I'm not gonna. I mean, I don't want. I mean, I want one answer for x. I mean, we're not gonna. So let's say we want one answer. What's the answer? It's all what?
If you're in the first loop,
Well, if you're in the first iteration, but if you're in the other iteration, it's the other one. But the point is, when we're going to produce one answer, it's going to summarize all possible executions, right? I mean, because we want one. I mean, at the end of the day, okay. Hold on. Let's just ground ourselves with an example. If I want to basically do constant propagation, remember how this is like our this is an example, but it's just useful to think about. And I want to use these reaching definitions. The way I did it before is I look up this. Let's assume there's no loop here, and I look up all the definitions. And let's say that thing is x equal 5, then I can put 5 here. Okay. If I want to do that for this in the setting of a loop, then I want this to tell me that it can come from there, and it can also come from here, and it can also come from here, because I want to look up and make sure that these are also 5. That's the only the only scenario in which I could replace this with 5, right? So in fact, the answer I really want is that this could come from there, or it could come from here on other iterations, or it could come from here. Okay? Does that make sense? You don't need to be convinced. But yeah.
Is there going to be a difference in which edge you put that on? Like, is the edge coming in the cycle edge going to have just 4 on it, and then the loop edge is going to have 4 different?
Oh yeah, absolutely.
That's the distinction.
Right. So this edge I can't write right now. I'm writeless. So this edge, you're absolutely right. At this edge, what will the information be? The information will be that x is just from 1. Now, what will this edge say? 167. And then what's going to happen here? What is this? There's something hidden here. I'm not showing you. A merge node. A merge node will combine the two. We'll take the union, and then we'll produce some information right here. Now, I'm not. How am I going to do this? What? Absolutely. But let me just show you. So I can't. Unfortunately, if I had my pen, I would just go through this and try to see what happens, because right, we start with the information at the top. Right, and we're going to keep on going down, and then we're going to get to this point, and then what are we going to do, right? So the thing that we could do is we could just assume that this back edge doesn't exist. Okay? And what we'll do is we'll keep on processing the information, and then what will happen is this back edge will just put some, eventually we'll realize actually we were wrong, there really is a back edge, and that back edge does have some information on it. So that information will then come back here, and it'll basically get unioned in, and then we'll basically propagate more information, and then that'll come back there, and then we're going to propagate more information, that'll go back there, and then we're going to keep on doing this. Now, you should start getting worried here, because now we're going around in this loop. If we're not careful, and actually I can tell you, you could do this, if you're not careful, you're going to run forever. And in fact, you can run forever, because if you compute a lot of information, you could actually possibly be running the program. I mean, you could literally be like going in this loop, and you could just keep on running the program. If you do it in this case, actually, here's what's going to happen. You're actually going to reach a point where you'll reach what's called a fixed point, where everything will stabilize in this loop. And we will not add any more information. So what happens is on the first iteration, we get x is 1, y is 3, and p is 4. And then we go down with that information, right? So that information here, now what happens is we add x goes to 6, and we deleted this x goes to 1, right? And here, remember what happens, this star p is a mess, right? Because what happens with the star p, it basically makes us, so we still have x goes to 6, y goes to 3, p goes to 4, but on top of that we have to, x could possibly come from 7, y and p, they could all come from 7 now, right? And now this information, this set, goes back upstream here and gets unioned in with that information there, right? And what do we get? You get the union of this set and that set, which is that set right there, right? Is that right?
Right.
Yeah,
that's right. That was right.
And now, so now we have this thing here, and then what do we do? Well, now we can actually go down, and if you actually do it, you'll actually see that the state, you basically nothing changes. Well, actually, hold on. This set, right, what happens here? Well, this, you just delete, what do?
Just add.
Well, actually, you delete all, it's actually not entirely true, it's the same thing. It's not, I'm lying here, it's not actually true, because here what you'll do is you'll delete everything with relate to x and add x equals 6, so right after this, right here, you'll actually know that x comes from 6, right? You see that? Whereas in fact here I kind of lied, okay, but the point is what actually happens is once you actually go down and you union it back in with this guy here, the result you'll get is exactly this. And at that point, you know that you're done. You don't need to go again because you'll get the same answer again. Yes, wait, hold on. It's like the same line, sorry. Who goes first? Okay. Okay, you go first.
Won't it always stabilize in one iteration?
For reaching definitions or in general?
In general.
No.
Why not?
Okay, so here's why not. I mean, I can, the way we set things, okay, so if you notice what we're doing here, we're binding x to, so we're creating bindings from all these variables to numbers which represent the statement, okay? Let me change something in this representation. Instead of when I say x arrow 1, what I really mean is that x has a value 1. It has a value 1, okay? So now what I could do is I can actually create something that will actually literally execute the program. Like when I say x equal x plus 1, it'll basically compute the binding at, oh, x is 2 afterwards. And then when I do the union, I'll get x. So basically think about a loop where I can't write. I can write on the board, but do you guys try to use the board?
Yeah.
When do we use that other than executing the actual program?
What?
When would we do such kind of analysis that you're actually assigning values to it other than when you're actually executing?
Constant propagation. In constant propagation, that's exactly what we do. Right? I mean, that's exactly what we do. We try to figure out, oh, this x is 5, and this y is 10. And if we're not careful and we kind of do it in a weird way, then we may end up kind of executing the program, and actually it'll just run forever. Okay, I don't need to use the board. In terms of reaching definitions,
I mean, the loop is the same, the static code is the same, so nothing will change no matter how many times we go.
well, so, I mean, right, I mean, so, right, so, you may actually, I haven't thought about the details of exactly how many iterations, so, we'll see later on what's the worst case scenario. Part of the problem here is that the question is whether you're making these statements regardless of what the flow functions do, or are you talking about the flow functions? Because the question is, if I write different flow functions that may be less or more precise, can I get something that actually may end up, you know, kind of creating this oscillating behavior? Right? I mean, that's really the thing that you're worried about, is that you have this kind of oscillating behavior.
I'm
What?
saying that if you know that you're in this case, right?
Right.
If you know that you're not in the first iteration, then you can take advantage by knowing that X is coming from 6, and I'm not in 7. But from iteration 2 and on, you know that X is coming from 6.
Right. So really, what you're saying is the reason why it's only 2 is because you can either come from outside the loop or within the loop. Okay. What happens if you have nested loops? That gets a little more tricky, right? When you have like 5 nested loops, each one. So now it's like, yeah, it's a little bit more. So maybe, I mean, you may actually still be right even in that scenario. But the point is that actually termination is a tricky issue, which we'll talk about at length. Actually, we'll talk about the theory, and I'm trying to understand how. I mean, that'll be one of our main things in terms of termination. That we'll read about termination. Actually, speaking of termination, let me actually I'll jump the gun here because I was planning on talking about this later, but since we're talking about termination, why do we care about termination? So is it really important? I mean, are we really worried about termination? I seem to have made a big deal out of it. Oh my gosh, we run forever. I mean, why are we so worried about termination? Should we worry about termination? Yes.
Because if we try and optimize and can't terminate, then that means we can't actually compile anymore. But if we could do a naive compilation and terminate,
Absolutely.
then we're no longer...
No, absolutely. I mean, obviously you want your compiler to terminate. I agree. But let's say, well, what's the standard? Okay, let's say I have something that runs a really, really long time. And actually, by the way, a lot of times when you implement this stuff, you actually will not. We'll talk about theoretical ways of proving termination, but in practice, people don't really prove termination. So, you know, the difference between non-terminating versus running a really long time is actually not quite, you know, it's very hard to distinguish. But what happens when you have something that really runs a long time? And in fact, this is a lot of times JIT do this, right? I mean, if you get a JIT and it takes too long, it's running for too long, what do? You just cut it off because it's stuck. Okay, right? I mean, you ran 5 times around the loop, stop. Just stop at 5 times. I mean, you just don't go 6 times. So, okay, why can we not do that? So it turns out the problem is we can't do that. That's the problem, is that we really can't stop this thing in the middle. We have to run it to completion. So there you see why we have to run this thing until we get the fixed point. Yeah?
Because you have less data and that's wrong.
Exactly. Because the way we set things up here is that we may actually get the wrong answer if we stop early. Okay? And these kind of analyses are called optimistic iterative data flow analysis, and we'll talk about the other version, which is a pessimistic analysis. A pessimistic analysis is an analysis where you can stop it at any point in time. Like any point, even like right after it stops, you stop it, like at any point in time you can stop it, and the results you'll get will be correct. You will get correct results. But the way we set things up here, this is what's called an optimistic iterative data flow analysis. You have to run it to completion, otherwise the results are not correct. And if we ran it once around the loop, totally wrong. Like, this information is completely bogus. Because it misses out the fact that, I mean, I would totally, I mean, people see that this is totally bogus? It's totally bogus. This would allow me to replace this with x equals 10 if that assignment were 10 without taking into account this assignment, which is just totally wrong. So termination, totally important, really important. Now, okay, we'll talk about termination. It's going to be a lot of fun. Termination is really cool. But so here's the way that the general way to do this kind of data flow analysis. So what we actually do is we're going to initialize. So we have all these variables, and you actually, in this case, you know, I named them like VI through V16. In reality, you can have an array of them. Okay, by the way, the reason why you should pay attention to this is not only because this is the coolest thing ever, but also in your project, in your second part of the project, you guys are going to implement this algorithm. Okay, this is your data flow analysis framework. This is what it's going to do. So you basically initialize all the DIs to the empty set. We're going to store all workloads, all nodes in a work list. Work list is just a list of nodes that we still have to process. And what we're going to do is, while the work list is not empty, so while we still have things to process, we're going to remove some nodes from the work list. We're going to apply the flow function to that node. And where do we get the information? So we have a node, we have some incoming information. Where do we get that incoming information from? Well, we have all the DIs, right? We're storing all this information already. So we can look up all the information, apply the flow function. That'll give us the output, and then we just update our DIs appropriately. And what do we do then? We actually add nodes whose input has changed back onto the work list, right? So you updated some DIs, and some nodes have this DI as input, so those nodes need to go back on the work list. Does that make sense? I can't just draw it. I would have like drawn it for you, but okay. This is it in code, in pseudocode. So we have the map from edges to the computed values of what the thing you want to solve for at that edge. A work list, and basically what you do is first you initialize every edge in the control flow graph to the empty set. You take every node and you add it to the work list. While the work list is not empty, just remove any node. Actually, turns out that once you have this set up here, well, actually, we'll talk about this in a second. I mean, it turns out that this algorithm works. You just remove any node. Just take any node. You basically will. Okay, this is a little bit confusing. So what I'm doing here is I'm taking what is n, what is n? Oh my God, the node. Incoming edges are. So again, I'm just generalizing it. Let's say that n has a list of incoming edges. There's not just one. In some cases, you might have two. And what this does is that m of this, it's like a map. It's like a map function, right? It takes this list and applies m on every list, every element of that list. So basically, what I'm getting here is I'm getting all the incoming information for that node based on this current map. Okay. Then I apply the flow function f on n with this node and the incoming information. And now that will give me, it'll give me an array of output information, one for each outgoing edge of n. And then what I do is I go for every I, which is in this kind of length thing. Okay, this is confusing. So basically what I'm doing is I'm looking up the information that I have for that ith edge in M, which is my current solution, and I'm comparing it to what I got from the flow function. Right, you see this here is what in M at that ith outgoing edge, and this is the information I got from the flow function at that ith edge. And if they're different, then I update the information and I basically take the other node, the node that's on the other side of this edge, and I add it to the work list. I really like this drawing from the. Okay, folks, I'm going to use the board. The problem is, I think people down there can not see what's on the board. Let's actually turn this top board. Can you guys see if I draw here? Okay. So basically, we have a node. And it has a whole bunch of incoming information, and we basically apply m. M is our map that tells us for every edge what each information is, right? So I'm going to apply m on each one of these things, and I'm going to get an array of inputs. I'll pass it through the flow function. That'll give me an array of outputs. I go to each one of these outputs that I got, and let's say I'm at this one right here. That's the ith one right here. And what I do is I look up the output I got from my flow function, and I look up the output, what I have in M for this edge. And if they're the same, I don't have to do anything. I'm done, right? There's nothing else to do. But if they're different, then I update my M with the information I got from the flow function, and I add this other node that's connected here to the work list. Because now this node needs to be reanalyzed. Its input changed, right? So, here's the thing. If you didn't follow this, don't worry. You you will, believe me, by the end of it, I mean, you will know this, and you'll have to implement it. So you will really have to kind of internalize how this works. And there's nothing like implementing this that you really understand what the work is like.
The more efficient, you just did everything here. Make sure you know that something you need is calculated before accessing it.
Right, well, so here's what's nice about this. I mean, what's nice about this is that it's such a clean and simple algorithm, and it works in the face of loops, it works in the face of, I mean, I don't have to care about, I mean, it's really cool that this works for, I can process them in any order I want, as long as I keep on processing them, and basically what will happen is eventually, your worklist, if things stabilize, your worklist will become empty, right?
Because you're basically adding nodes back and recalculating.
Right. Now, of course, one of the things is that this remove any, in general, you don't want to just remove any, because what will happen is, you may end up, so, if you have a control flow graph, I mean, as you mentioned, right, I mean, you want to basically first do the node up here before this node, because if I choose the last node to analyze, the last node in the control flow graph, but I analyzed that, and I feel very proud of myself, I did it. And then it's like, well, hello, like the input of that node is probably going to change. In fact, actually, if you analyze the last node first, what's the input going to be? It's going to be the empty set, right? Because we initialize everything in the empty set. So it'll probably produce the empty set out, which is totally bogus. So eventually, this will change and become different. So yes, you're absolutely right. There is an ordering here that you'd like to kind of follow. So are there any specific questions? So if you didn't understand this, are there specific questions that you have right now that you want clarified? Huh? No? So either all of you understood it, or so either you don't, or you didn't understand, or it was so bad that you don't even know what question to ask. It's like, oh my gosh, it's so bad. It's okay. I'll see. Yeah, we'll see when the project comes. That'll sense your understanding of it. So the ordering, that's one of the things so there's two issues here with this worthless algorithm: ordering and does the algorithm terminate. So in terms of ordering, so the simplest thing you can do is topological order, assuming backends have been removed. There's more advanced things you can do, but that actually kind of works relatively well. Right, I mean, you basically do a topological order, and basically what you do is you want to remove nodes that come first in this ordering. But if you get the order wrong, what will happen is, it's not that you'll get a different answer. You'll get the same answer, it's just it'll take longer to compute. So yeah. So, cool, we already talked about this. This is great, so we don't need so we can't stop the algorithm in the middle. Termination is really important. And what we'll do is next time, actually, do we have one more minute?
Just one.
Just 1 minute?
What?
So, because we only have one, so what I want to, I'm not going to do this now, but the idea, you can actually, maybe, if you want to think about this, what I want, or you can look up the answer, no, don't look up the answer on the slide, because that's not fun. But what we like to think about, if you guys could have some time, is what would be a way to make this, so this is, I don't want to talk about, now we're not talking about, what is it called? Reaching definition, right? Notice that we've changed, now this is a flow function. We've changed kind of things, I mean, now we're very abstract, right? I mean, this could work for almost anything. I mean, it's a very general algorithm. So how can we make this thing terminate? And let's say for the case of reaching definition, let's say we want this to terminate no matter how you write the flow function. No matter what the flow function is, no matter what the flow function, you can write like the craziest flow function. I want to guarantee that this loop terminates. Right? How would you do that? How would you modify this loop so that it terminates?
Saturation or something. Make a counter of saturation that after this much looping around stuff.
No, it's
No, we can't do that. That's the problem. We can't stop in the middle. This is the thing. It's horrible. It's like you can't stop in the middle because you're going to get the wrong answer. You're not guaranteed that. You have to get it until you reach a fixed point. Otherwise, you may not get the right answer.
Yeah. I could write a program that they were doing this for constant propagation. I could write a program that never terminates.
Yeah.
No,
So that this would never terminate. If it's
No.
it is guaranteed to terminate.
With this?
Yes. Okay.
No, it's not. I mean, there's no guarantee.
If I wrote a program that it doesn't terminate.
No. Whoa. Totally not true, because for constant propagation, and we'll get to this. No, when you do constant propagation, you have to do it carefully. So, I mean, when you do it, I mean, you know, if you have, like, say, for example, a simple program that says x equals 0, and then inside the loop it says x equals x plus 1.
Well, true, x equals x plus 1.
Yeah, so what will happen is the first time around the loop, x will be 0, and then the next time around the loop, x will be 1. And now what we'll say is x is not constant. Right? We'll learn that information, that x is not constant, and we will stop tracking x. So, I mean, of course, if you just keep on saying, oh, x is 0, now x is 1, now x is 2, that's going to leave you run forever. Absolutely. That's why we have to be a little bit more clever, and we have to design the flow functions very carefully. That's why this shows why, if you're not careful.
For termination, you could say that we're not going to repeat if something is changing itself.
Right, but what I want to do here is I want to think about specifically, what is it called? Reaching definitions, and how do we make, you have an idea.
I mean, the idea was never, whenever you update that, always union, previous set, and then...
Absolutely, it's actually a simple idea, but it actually works. Right, so basically what's happening here is that we compute new information, and then we update this thing directly. Instead of updating it, what we could do is union it in, and then what happens? We will never go down. We'll start with the empty set everywhere, and then we'll always go, either stay the same or go up. We'll never go back down. And actually, if you just, because there's only a finite number of variables and a finite number of segments, there's only, you're bounded, if everything is finite, you're bounded by a set on the top. So eventually, by just keep on going up, eventually you will reach something that will reach fixed point, right? Either, if you want to reach a fixed point, you have to keep on growing every time, and eventually you will just reach this ceiling, right? So that's exactly right. And what we do is it's this. Basically, we get this new information, we get the old one, we union it in, and then we basically do the test. Last thing, the reason why this sucks is because now we've actually introduced this union operator. And for a variety of reasons we're going to talk about next time, we want to get rid of that union operator. And we'll see how to do that using lattices. So that'll be the next thing we'll talk about. Okay, cool.